We're going to start with a talk by David Pollan from Yale about bootstrapping the humongous CFT landscape. But yeah, David, thanks for agreeing to giving a talk, and the floor is yours. I'll give you a warning after 45 minutes. So it's like roughly an hour with questions, but it's flexible.
Okay, sounds good. Thank you very much for inviting me to give a talk at this interesting conference. I've been enjoying it over Zoom. My apologies for not being there in person. Yeah, I was hoping to tell you a little bit about some of the progress that we've made in the conformal bootstrap approach to conformal field theories and critical phenomena and quantum many-body physics, which is, I guess, the topic of this conference. I guess you've heard a few bootstrap talks already here, but let me just highlight that there are a number of different targets for the conformal bootstrap that we have in mind. These include the critical three-dimensional ON models that you've heard a little bit about. They also include models of interacting fermions, like the three-dimensional Gross-Neveu-Yukawa models. I'll talk more about those models a little bit later. And they also include gauge theories like three-dimensional QED, Chern-Simons theories, four-dimensional QCD, and these all are ways of constructing interesting interacting conformal field theories that one could potentially try to solve using bootstrap methods. Of course, all of these models also have interesting supersymmetric extensions that one can try to solve. And also another hope for the bootstrap is that it might be some tool that could be used to discover previously unknown conformal field theories, perhaps ones that don't have any simple Lagrangian description. Okay, so okay, I won't dwell on this. You've heard about the basic ideas behind the bootstrap. The hope is to use symmetries like conformal symmetry, crossing symmetry, and constraints like unitarity in order to isolate and solve conformal field theories. And concretely, this takes the form of some rules, which you obtain by taking 4-point correlation functions and expanding them in different OPE channels. And this tells you that a sum of conformal blocks in one channel has to equal a sum of conformal blocks in a different channel. And in particular, if you look at 4-point functions with all identical fields, these conformal block functions have positive coefficients. They're the squares of OPE coefficients. And then you can try to take advantage of these positivity properties of the fact that unitarity gives you bounds on the scaling, lower bounds on the scaling dimensions, and ask when can this sum rule be satisfied. And over the last decade or so, we've been developing kind of a powerful numerical approach to studying these crossing relations, which basically asks, okay, we're trying to sum up a bunch of functions, which you can think about as being like vectors in a vector space, with positive coefficients to get 0. And you ask, when can you do this? You can do it in general when all the vectors are pointing in kind of random directions and they can balance each other off to get the 0 vector. But you can't do it if they're all pointing to one side of some kind of separating plane. Then you can't add them up with positive coefficients to get the 0 vector. And so the basic numerical approach is to use convex optimization methods to look for these kinds of separating planes, perhaps after making some assumptions about the spectrum. And if you can find this kind of separating plane that puts all the vectors to one side of it, then you learn that whatever assumptions you made are incompatible with crossing symmetry and unitarity. And so now there's a kind of a whole suite of software tools that have been developed to solve these kinds of problems. You can find some of them in this software repository developed by Bootstrap collaboration. These tools have led to some exciting results, like small islands for the three-dimensional Ising model and O2 vector models that are shown here. You can see on the right that the best island for the O2 vector model is kind of beautifully compatible with recent Monte Carlo simulations. And so it seems like this method is working quite well. So to kind of push things forward, there have been kind of several recent advances in the last couple of years. One of them has been the development of a software tool called Blocks 3D, which is aimed at efficient computation of spinning 3D conformal blocks. So if you have 4-point functions of operators with spin, and you want to compute all the conformal blocks for arbitrary exchanged operators, this software allows you to do it efficiently and in complete generality in 3 dimensions. We've also developed some algorithms for searching through kind of large multi-dimensional parameter spaces. These islands could, live in kind of high-dimensional spaces involving multiple scaling dimensions, multiple OPE coefficients. And so we've developed some algorithms for efficiently searching through those spaces. There's also this beautiful navigator method that you heard about on Wednesday, which is aimed at both finding these islands in the kind of allowed space of scaling dimensions, and it can also be used to extremize scaling dimensions or OPE coefficients over the island. So it's kind of a very, very useful method. And on top of that, there have been kind of improved software tools for solving these semi-definite programming problems used in the Bootstrap, for software tools for implementing the navigator method, software tools for extracting kind of the extremal spectrum of the solution on the boundary of the allowed region, and some experimental semi-definite programming solvers, which use a technique called outer approximation. So these are all kind of newly developed tools that are just being explored now. Okay, so one application of these new software tools was to kind of a large system of correlators in the 3-dimensional O3 model. And so we studied the system of crossing relations involving the leading O3 vector, phi I, the leading singlet S, and the leading 2-index symmetric tensor, Tij. This leads to a system of 28 crossing relations, and involves kind of scanning over a 6-dimensional parameter space involving these 3 scaling dimensions, as well as 3 ratios of their OPE coefficients. But by searching through that parameter space, we mapped out this island, which you can see is kind of the Bootstrap island is in black, compared with results from Monte Carlo simulations. And you can see that they're kind of beautifully compatible with each other. One other question we kind of honed in on in our Bootstrap study is the question of whether the leading 4-index symmetric tensor, which I call T4 here, is relevant or irrelevant. This is a physically interesting question, because if you have, say, a Heisenberg magnet with some cubic anisotropy, then this operator T4 can get generated through renormalization group flow. And if it's relevant, then it can potentially induce a flow to a fixed point with cubic symmetry rather than a fixed point with O3 symmetry. And so this has been kind of an interesting question that people have studied over the years. The Bootstrap gives you a very kind of sharp way to ask and try to address this question. And so, one thing we did with these new search strategies, this algorithm called TipTop, is basically search over this island and ask, what is the maximum possible value of the scaling dimension of this operator T4 over the island? A slice of that search is shown in this plot on the left. And what we found is that the maximum scaling dimension is 2.99, slightly larger than 2.99. And so we basically, from this, can obtain a numerical Bootstrap proof that critical Heisenberg magnets should be unstable to cubic anisotropy. So So perhaps only very slightly so. Okay, so that was one recent application of these methods. In this talk, I kind of wanted to focus on new results. Yeah, is there a question?
Yeah, regarding the result for delta 4.
Yeah.
Do you have a comparison with other methods, for example, Monte Carlo?
Let's see, I'm trying to remember if there have been Monte Carlo results for delta T4. Yeah, I don't completely remember. I know, people have estimated it using the large N expansion and epsilon expansion methods. And there are a variety of previous results which have pointed to this scaling dimension being slightly relevant, though if there are some results which have come on the other side of it.
The other methods, the field theory methods,
yeah,
show that it's irrelevant or relevant. I misheard.
Most of the recent ones have pointed to it being relevant.
Relevant. In the bootstrap, you're showing it's an upper bound. Is there a closure to this green island or from below? From below,
yeah. That's a good question. So this is something that we still want to study further. I believe that if you assume a gap between T4 and the next 4-index symmetric tensor, then you should be able to get a lower bound on delta T4. But precisely how strong that lower bound is and how sensitive it is to the gap, I don't know right now. So I think that's an interesting question for the future. Good, thanks. Are there any other questions? All right, so I wanted to focus on models involving fermions. So these are sometimes called Gross-Neveu or Gross-Neveu-Yukawa models. And so the simplest way to construct this kind of model is to take n fermions in 3 dimensions or 2 + 1 dimensions and couple them to a scalar field sigma through a Yukawa type coupling. And in general, sigma could also have a quartic coupling. And at large n, you can establish that there's a fixed point perturbatively in the 1/n expansion. And at various small values of n, there are kind of interesting applications of these models. So for example, there have been proposed applications to critical points in D-wave superconductors, possible critical points in graphene. There are applications to models of at n = 4 to spinless fermions on a honeycomb lattice, or models of phase transitions in gapless semiconductors. So there are various possible applications. Maybe I should mention that here I'm counting the number of fermions by counting the number of 3-dimensional Majorana fermions. So these are real 2-component spinors. And of course, different people have different conventions for what kind of fermions they're counting. But here I'm counting Majorana fermions. Now, I should also stress that there are kind of lots of different variations on these models. So there are variations involving multiple scalar fields. There are variations involving fermions with different kinds of couplings to the scalars. And so in particular, one distinction I want to draw your attention to is that there are kind of two, if you have n Majorana fermions, there are kind of two distinct but closely related fixed points you might want to think about. One of them is where all n of the Majorana fermions have the same sign coupling to the scalar sigma. And the other is where half of the Majorana fermions have an opposite sign coupling as the other half. And so in the first model, where all of the Majorana fermions have the same sign coupling, there's an ON global symmetry, which rotates the Majorana fermions into each other. And in the other model, there's a different symmetry. It's an ON/2 cross ON/2 symmetry, rotating each set of fermions into each other, combined with a Z2 symmetry, which flips sigma, sigma goes to minus sigma, and flips psi L with psi R, so flips, exchanges the two sets of fermions with each other. And these two models are very similar in many respects, but they describe kind of different physics. This ON invariant GNY model describes a kind of topological phase transition in which the expectation value of sigma breaks a time reversal symmetry. So under time reversal symmetry, sigma goes to minus sigma. It's a pseudoscalar, and psi bar psi goes to minus itself. And the other model, which is sometimes called the chiral Ising GNY model, that describes a Z2 breaking transition that preserves a time reversal symmetry. And so they kind of describe different physical scenarios and have different potential applications. But they're quite closely related. And in particular, if you kind of look at the leading scaling dimensions or leading critical exponents in these models, so the scaling dimension of sigma, scaling dimension of psi, scaling dimension of epsilon, which is like sigma squared, then you actually have to go to kind of for loop order in order to see a difference between the two models and get sensitive to this difference in sign of the Yukawa couplings. And so this means that we expect the difference in these leading exponents to be quite small between the two models. If you kind of plug in numbers, for example, in the epsilon expansion, you can estimate that the difference in scaling dimensions should be at the 10 to the minus 5 to 10 to the minus 6 level. And so it's kind of an interesting question of whether the bootstrap can resolve the difference between the two models. It's also, something to keep in mind because there are some, we're going to study the ON GNY models using bootstrap methods, but there are also Monte Carlo simulations which study these chiral Ising GNY models. And so we can still potentially try to compare the results against each other because we expect the difference in exponents to be very small. Okay, so I'll say something about the ON GNY models in a moment. But then if you go all the way down to n equals 1, and you have one Majorana fermion and one real scalar, then this is kind of the minimal GNY model, and it's also a model that we believe has emergent three-dimensional curly n equals 1 supersymmetry. And so you can capture this model using a theory with a cubic superpotential, sigma cubed. And this model is also kind of interesting because, for example, there's a proposal by Grober, Sheng, and Vishwanath that this could be potentially realized as something which lives on the boundary of 3+1 dimensional topological superconductors, whereas boundary supports a propagating 2+1 dimensional Majorana fermion. Okay, so let me first show you some results for this model. Because it has supersymmetry, we can kind of take advantage of the supersymmetry and impose, for example, that the scaling dimension of the epsilon operator is equal to the scaling dimension of sigma plus 1. And also impose that there are various relations between the OPE coefficients of these operators that you can work out. And so plugging that all into the bootstrap and looking at the mixed correlator system involving 4-point functions of sigmas and epsilons, that actually leads to a very kind of small island in the allowed parameter space after assuming that sigma and epsilon are isolated. Here we're also the y-axis. So the x-axis here is delta sigma. The y-axis is delta sigma prime, the second odd scalar field. And then we also assume that the sigma double prime operator is irrelevant, has a scaling dimension greater than 3, as well as the epsilon prime operator. And so under those assumptions, combined with supersymmetry, you get a very small island with the error in the fifth to sixth decimal point for delta sigma. And these results kind of compare nicely to results from, or estimates from, the epsilon expansion, resummations of the epsilon expansion by Ihrig, Michaela, and Scherer, which has larger error bars, but seems to be compatible with our result. Across this island, we've also computed bounds on the leading OPE coefficient, so delta sigma sigma epsilon, and we can get a
David,
yep.
just a quick question about delta sigma. Isn't that
Yep.
fixed by Susie?
Isn't it fixed by Susie?
Yeah.
No, it is not.
It's not. Okay.
So in the
n equal 2.
curly n equals 2 model,
Yeah.
there's some holomorphy. There's a complex scalar. There's an R symmetry, and
Exactly.
using all those things, you can fix the dimension of sigma. But in the curly n equals 1 supersymmetric model, you can't. Yeah.
Because I remember also there was a bootstrap paper on this n equal 2 Susie theory by Dalimil, Mazach, and colleagues.
Yeah.
And they were assuming Susie in the bootstrap, and here, yes, you're also assuming n equal 1 Susie in the bootstrap.
Yep, that's right. That's right. But it's weaker. N equals 1 Susie is weaker than n equals 2 Susie. Yeah. So in the language of these Gross-Neveu-Yukawa models, this n equals 2 model has a complex scalar field. So there are kind of two real scalars which have interactions with a complex two-component fermion. So it's just a slightly bigger model compared to this one. Okay, so but here's Susie still helps. Organizing things into supersymmetry multiplets still helps, and something else that we were trying to understand is what the whole kind of spectrum of kind of leading operators as a function of their spin looks like. So, in general, you can think about what are sometimes called double twist operators. So these are operators like sigma, L derivatives, sigma, composite operators with spin L. There have also been recent kind of analytical techniques which let you calculate the scaling dimensions of these double twist operators at large spin. So if you study the bootstrap equation in a light cone limit, where two of the operators become light-like separated from each other, you can develop an analytical large spin expansion, which relates the anomalous dimensions of these operators to the leading operators and leading twist operators in the spectrum, like delta epsilon. And then a few years ago, there was a kind of upgraded version of this called the Laurencian inversion formula, which gives you a method to compute kind of some all orders resummation of this expansion into an analytic function, which can be computed by integrating a certain double discontinuity of the 4-point function. In practice, these integrals can be done in terms of some kind of 4f3 hypergeometric functions. And so this gives us kind of a powerful way to approximate analytically what the spectrum looks like. So just to show you that these methods work, here, we used a numerical bootstrap method called the extremal functional or extremal spectrum approach, where we maximize this OPE coefficient, and right at its maximum value, there's kind of a unique solution to crossing symmetry that you can reconstruct, and that's what's shown in these dots, these red dots and green dots, these are showing kind of the two leading trajectories of operators in this n equals 1 supersymmetric Ising model, or minimal GNY model, and the lines show the these analytical computations using the Laurencian inversion formula under various assumptions about which operators you include to approximate the 4-point function. And basically what this plot is showing is that as you include more and more operators, you get a better and better approximation to the 4-point function. This analytical curve gets kind of closer and closer to the numerical data as a function of spin. And it works all the way down to low spin. So this operator down here at twist 1 is the multiplet containing the stress tensor. So we know exactly what it's. Okay, so I'm not going to delve too much into the details here, but I just want to show you this is an interesting comparison that we can do, and that this is kind of a fun playground for developing analytical methods. Okay, so let me focus now on the ON GNY models, which don't have any supersymmetry. And so we started to study the bootstrap for 4-point functions of fermions a few years ago in 2017. And so kind of our earlier plots looked something like this. So we looked at 4-point functions of psi I, psi j, psi k, psi l, where psi is a vector under an ON symmetry, and computed a bound on the leading 2-index symmetric tensor, psi I, psi j, which here we're calling sigma t. And what you can see is that for different values of n, that bound has a kind of kink in it. They basically follow the same curve and then branch off at some point where there's a kink in the bound. And at least at large n, like n equals 10, n equals 20, the locations of those kinks match pretty nicely to the computations in the 1/n expansion for the GNY models. So it looks like these kinks were kind of physical, and you could at least conjecture that going down to small n, the locations of these kind of branch points still coincide with the physical GNY models. Okay, so and you can also look at what the allowed region looks like in the delta psi, delta sigma plane, and so you kind of get an intricate structure, some intricate lower bounds. If you assume that sigma prime is irrelevant, so namely sigma is the only relevant parity odd scalar in the spectrum, you get some kind of interesting wave structure. There kind of has some kinks, and it looked like the locations of some of these kinks were kind of matching pretty nicely to estimates in the GNY models. But of course, this isn't this story gives us kind of a bootstrap way to estimate these dimensions under a kind of conjecture, but it's not on very solid ground. But there was a nice comparison that was done by Ihrig, Mihaela, and Scherer, comparing the locations of these bootstrap kinks to other methods like resummations of the large n expansion, resummations of the epsilon expansion, functional renormalization group methods, and Monte Carlo. And you can see that for the exponents eta phi and eta psi related to the scaling dimension of sigma and psi, there's a pretty good agreement between the bootstrap results, which are these red diamonds, and the other methods. On the other hand, in our earlier bootstrap study, we also used this extremal spectrum approach to try to estimate the scaling dimension of the epsilon operator, the sigma squared operator, which is related to the new critical exponent. And there, the estimates that we got from this kind of non-rigorous extremal spectrum method were very different from the results coming out of methods. So this has been kind of a puzzle, and kind of motivates trying to put these bootstrap calculations on a firmer and more rigorous footing. Okay, so that's been motivating us to kind of extend these fermion bootstrap calculations to a bigger system of correlators, and see if we can try to get more rigorous islands for these GNY models. And so what we've been doing over the last couple of years is looking at the bootstrap system involving all 4-point functions containing the fermion psi, the pseudoscalar sigma, and the scalar epsilon. This leads to a big system of 38 crossing relations. There's also been a nice application of this new blocks 3D software, because you have to calculate lots of conformal blocks involving spinning operators and Lorentz tensor structures for the fermion. Basically, we looked at this system of bootstrap equations. We imposed some gap assumptions motivated by our expectations from the large N expansion, and kind of search for allowed points in a 6-dimensional parameter space involving these 3 scaling dimensions and 3 ratios of OPE coefficients. And just to kind of flash what the large N calculations look like, you can kind of make a table of all the leading operators in the theory. There's psi, sigma, and epsilon. There's the 2-index symmetric tensor, psi I, psi j. There's the sigma prime operator, which is like sigma cubed. There's the epsilon prime operator, which is like sigma del squared sigma. There's also a sigma to the 4th operator. And then there are various kind of subleading fermion operators like sigma squared psi and sigma cubed psi. Notice that there isn't an operator like sigma psi in this list, because that operator is essentially removed by the fermion equation of motion in the large N limit. And so in particular, you kind of expect a gap in this spectrum of fermionic operators that have opposite parity to the leading fermion psi. So I'm calling this the chi sector. We can take advantage of that gap in the spectrum using the bootstrap method. So at large N, it's this scaling dimension of chi starts at 4 plus 1 over N corrections. And so we can impose a relatively big gap in that sector. Okay, so here's what our results look like. So this is showing the delta psi, delta sigma plane. For different values of N, we were able to successfully compute small bootstrap islands using this sigma psi epsilon system, and some gaps in the spectrum motivated by the large N estimates in this equation of motion and delta chi. And so you can, so the bootstrap islands in this plot are kind of little dots, which I'll show you some zooms of them in a moment. You can see it's a bigger island for N equals 2, but the island gets really small at larger values of N, like N equals 8. And this plot, I've compared these little bootstrap islands to estimates from resummations of the epsilon expansion, shown in these boxes. So you can see that they're relatively close to each other, though not completely overlapping. Also, this dashed line shows you the large N curve that you get from the 1 over N expansion. So let me show you some kind of zooms in of these results. Oh, sorry, before I get there, you can also make this kind of plot in the delta sigma and delta epsilon plane. So you can see what the bootstrap islands look like in this plane. And in particular, you can see that now that there's quite good agreement between the bootstrap calculations of delta epsilon and estimates from the large N expansion. So they're basically now overlapping. And so this completely resolves this discrepancy that we saw previously using this extremal spectrum estimate compared to the other methods. Good. So let me just zoom in a little bit. So here's a picture of our O8 island compared to the epsilon expansion results, and also computations using Monte Carlo simulations by Liu, Wang, Sun, and Meng. These were computations for a system which should be in this chiralizing GNY universality class, but as I mentioned before, we expect the exponents to be quite close to the ON GNY models that we computed. And so you can see that, the kind of calculations agree pretty well for delta psi, and they're overlapping for delta psi, but they're kind of a little bit off from each other in delta sigma. So kind of understanding the source of that disagreement would be interesting.
David, one second. There's a question in the
Yep.
audience.
Yeah.
Can you hear me?
Yes.
Yeah. So why the exponents should be the same for the chiral as for the ON? What is it? Why do you just expect that, or you can show that, or you can just?
They shouldn't be exactly the same.
But why do you say, why do you justify? How do you justify the comparison?
Yeah, that's what I was. Let's see. I tried to.
Sorry,
So the justification is that in the perturbative calculations, like that you would do in the epsilon expansion or the large N expansion, you have to go to for loop order to see the difference in these exponents.
Perfect. Yeah.
Yeah. And so, plugging in, N equals 2, 4, or 8 to these calculations, or basically gives you the estimate that the difference should be at the 10 to the minus 5 level.
Okay.
So that's the reason for that expectation.
Why can you not do the calculations for the chiral case? Is that possible for you to do?
No, it should be possible.
Okay.
It's just it requires setting up a different bootstrap system, which is a little more complicated, and we haven't done it yet. Yeah, so I think that's an interesting thing to do kind of next, is kind of generalize these bootstrap computations to the chiral model and see, we're basically, we're kind of getting error bars which are at the 10 to the minus 5 level for delta psi. And so you might think, maybe we're at the level in the bootstrap where we could resolve the difference between these two scaling dimensions. So I think that would be an interesting thing to do. Okay, here's what the results look like at N equals 4. Also compared to some quantum Monte Carlo simulations by Huffman and Chandrasekaran, also for the chiral model. But you can see that there's pretty nice agreement between the bootstrap island and the Monte Carlo region, and it's also close to the estimates from the epsilon expansion, though delta sigma is again a little bit off. And then here's what it looks like at N equals 2. Here there was a recent kind of Monte Carlo study by Tabe, Nagari, Masiejko, and Vezi for the O2 GNY model, and you can see that there's pretty good agreement, very nice agreement there, though it's a bit off in delta epsilon. So that's something to pay attention to. Okay, so and let me just highlight kind of one thing that you might worry about in these computations, is in doing these computations we had to impose a gap until the next operator in this sigma sector. So this is the operator that I'm calling sigma prime. It's like the sigma cubed operator. And for most of our computations, we assumed a gap of 3, that it was irrelevant, which is kind of justified by this large n calculations, show that its scaling dimension is 3 plus positive 1 over n corrections. So it's at least true at large n. On the other hand, when you go down to n equals 1, where was my island? When you go down to n equals 1, we know that delta sigma prime is 2.885. So it's slightly less than 3. And so at large n, it goes bigger than 3. And then at n equals 1, it goes to be slightly less than 3. So there's kind of an interesting question of what the trajectory of sigma prime looks like and whether it's justified to assume it's irrelevant at different values of n. And so, so first of all, to be conservative in these O2 models, we also computed our islands with a more conservative assumption that is bigger than 2.5. And also we kind of tried to get a picture of what the spectrum, the sigma prime operator is doing, basically by doing some, Pade approximation, which matches to the large n expansion at large n, and matches to the known results at n equals 1 for the supersymmetric model. And in doing those approximations, you get curves which look like this, which point to this operator being irrelevant all the way down to n equals 2, and then it kind of switches to being relevant at n equals 1. But this is just some kind of a Pade approximation, which is really like a guess for what it's doing, an educated guess. And so I think it would be interesting to kind of put this on firmer footing and try to get a more rigorous determination of the dimension of the sigma prime operator. And that's something we're trying to do now in the Bootstrap using this new navigator method that you heard about on Wednesday. And let me also just mention that, in this Bootstrap system that we studied for the GNY models involving psi, sigma, and epsilon, we can also study this n equals 1 model that I previously showed you the island for, which has supersymmetry. And so just using the same setup, using these fermionic correlators and so on, we can get islands for this n equals 1 model without assuming any supersymmetry. This is just kind of like a nice consistency check that our implementation should be working, but you can see that this island that we've gotten basically has a tip which just intersects the line expected in a supersymmetric theory. So this is the line delta sigma equals delta psi minus 1/2, or the line delta epsilon equals delta sigma plus 1. The tip of this island just intersects that. And so the supersymmetric model lives right in these lower tips. Another thing we did, which is kind of a fun application, is to ask, is this, to what extent is supersymmetry emergent in this solution to the Bootstrap? And so kind of scanning across this island, we can place an upper bound on the scaling dimension of the leading spin 3 halves operator. So this is the operator that would become a supercurrent in a supersymmetric theory, and it would have scaling dimension 2.5 in a supersymmetric theory. And we can see that there's an upper bound on the scaling dimension of this spin 3 halves operator, which is that it has to be less than 2.54 all the way across this island. So there's some sense in which, this whole island is approximately supersymmetric. It has an operator which is approximately a supercurrent, and it becomes exactly supersymmetric right at this tip. Okay, so in the last few minutes that I have, I just wanted to say a little bit about our attempts to apply bootstrap methods to gauge theories. And so there are lots of motivations for bootstrapping gauge theories. There are applications to 3-dimensional spin liquids and deconfined critical points. In 4 dimensions, there are applications to physics beyond the standard model. There are lots of interesting questions about conformal windows of gauge theories. They're involved in lots of dualities and so on. And so some concrete targets for the Bootstrap are a U1 gauge theory in 3 dimensions, QED3, where the number of fermions coupled to a number of fermions, NF, which is in the conformal window, which we can establish has a fixed point at large n, and we believe sort of goes down to some critical value of nf star. And so kind of studying that conformal window is interesting for QED3. And of course, another interesting target is, say, 4-dimensional QCD and its conformal window, which the Bootstrap hasn't yet been able to say very much about. Okay, on the other hand, bootstrapping these kinds of gauge theories coupled to matter is kind of challenging because you can only really use gauge invariant operators like fermion bilinears, 4 fermion operators, and so on. And so it's kind of challenging to distinguish different gauge theories from each other because you don't have very direct access to the gauge group. Okay, so some, I think, very interesting progress at bootstrapping 3-dimensional QED was made a few years ago by Chester and Pufu. They focused on kind of bootstrapping correlators involving monopole operators. So these are operators kind of corresponding to topologically non-trivial configurations of the gauge field. These monopole operators were charged under a topological current, J-mu topological, which is the dual of the field strength tensor. And at least at large n, you can kind of establish various properties of the monopole operators. For example, the lightest monopole, which in my convention says charge 1/2, has a scaling dimension of 0.265 times NF minus some tiny correction minus 0.0838. And so you can kind of use these large n calculations to try to estimate what the monopoles are doing at smaller values of n. Okay, so kind of my focus in the next few slides is going to be 4-flavor QED3, which is
David.
Yeah.
So your NF here stands for what? Because before you were counting Majorana fermions. Now.
Yeah, that's right. Now I'm counting the number of 2-component Dirac fermions.
Okay.
2-component complex fermions. Thanks. Okay, so I'm going to focus on the case of 4 2-component complex fermions, which is kind of one of the physically most interesting cases. It's kind of generally expected to be in the conformal window, though maybe near the bottom of it. And this is also a theory that has some relevance to physical systems, which are called Dirac spin liquids. And so, okay, so one thing we can do to try to get a handle on 4-flavor QED is kind of look at all these large n calculations and plug in NF equals 4 and see what happens. And this, this gives you some kind of way to estimate the spectrum of the theory. And so here in this table, I'm just showing some of the leading operators in the large n limit. So there's the kind of leading singlet operator, which has a scaling dimension around 3.6 if you plug in numbers. There's a leading fermion bilinear adjoint psi bar psi. That's something that I'll call R later, which is one of the lightest operators. It has a scaling dimension of 1.46 if you plug in numbers. And then there are also the monopole operators, like M1/2, which we can estimate has a scaling dimension 1.022. M1, the charge 1 monopole, has a scaling dimension of 2.498. And so those are going to kind of play important roles in our bootstrap studies. And let me also highlight that there's kind of an important role played by certain 4 fermion operators.
Sure, I have a question.
Yeah.
So these monopole operators, they're not the bare monopole operators, right? They're dressed with, like in a state operator correspondence, they're dressed with fermion bilinears.
So that's right. So at each charge, there's value of the charge. There's some bare monopole that you can think about. So M1/2 is a bare monopole. But there are also monopole operators that are kind of dressed by fermions. So yeah, those operators all exist, both the bare monopoles and dressed monopoles.
Okay. Can you also do this if there's a Chern-Simons term present?
Yes. Yeah, that's right. So there are, I mean, this paper, for example, by Chester, Iliescu, Mizet, and Pufu calculated scaling dimensions of monopoles in Chern-Simons theories at large n as well.
Thanks.
But in what I'm talking about, I'm not gonna touch Chern-Simons. Okay, so I just wanted to mention that there's kind of an important role played by certain 4 fermion operators. So for example, you can build an operator, which I'm going to call AA bar, which looks like psi bar psi, and has 2 SUN indices, which are anti-symmetrized, and 2 fundamental indices, which are anti-symmetrized, and 2 anti-fundamental indices, which are anti-symmetrized. So A means anti-symmetrized. So that operator actually plays an important role. And in this large n estimate, what happens is that it starts its life at scaling dimension 4. It gets a big negative correction, which brings it down to 2.38. And so there's kind of an open question right now whether this operator is relevant or irrelevant at small values of n, like n equals 4. And that's kind of a physically interesting question. Okay, so in this work by Chester and Pufu, they placed a bound on the charge 1 monopole operator as a function of the charge 1/2 monopole operator using bootstrap methods. You kind of get an interesting upper bound, which sits relatively close to the large n estimates of these scaling dimensions, which are shown in this X on the left plot. And they also saw that you can kind of get a sharp cut on this allowed region if you put in a gap until this AA bar operator, this 4 fermion operator. And the location of that cut is kind of very sensitive to what gap you put in for AA bar. So so that's one kind of interesting feature here. And they also noticed that if you isolate the leading charge 1 operator, so you impose a gap above it, say of 2.8, 3, or 3.5, then you can carve out, some kind of peninsula region in this plane. And so, you can make the conjecture that the tip of this peninsula might be kind of near the physical 3D QED solution. Okay, so on the other hand, in kind of computing these things, they assumed that this AA bar operator was irrelevant, which I don't think is on kind of firm footing yet, especially because the leading large n correction makes it have a dimension of 2.38. And other gaps motivated by all this kind of knowledge of the spectrum weren't used in this study. So we were kind of motivated to kind of push this further and see if we could get closer to the physical QED solution. And pushing it further means kind of using more strategic gap assumptions as well as considering mixed correlators. Now, there was also a nice study that came out recently by Yin Chen He, Junchen Rong, and Ning Su, which indeed looked at mixed correlators involving the psi bar psi and M1/2 correlators. And they basically kind of input a conservative set of gap assumptions in the AA bar, SS bar, and singlet sectors under the assumption that this theory could be realized on a triangular lattice. So these operators are all allowed to be generated if by the symmetries of the triangular lattice. So they assume they're irrelevant, and making that set of assumptions basically carves out some some box-like region, which actually kind of rules out this large N estimate, but allows for an estimate of delta M1/2, which came from a recent Monte Carlo simulation by Karthik and Narayanan. Okay, so this is one way you can approach the problem. It's very unclear how you given these kinds of assumptions, how you'd isolate the QED solution. Now our group kind of pursued took a different perspective, and we thought maybe we should see what happens if we get more aggressive with our gap assumptions. And so one thing we looked at is what happens if we kind of make this gap until the M1 prime operator even bigger. So here in this table, the second operator above M1 with the same charge and quantum numbers, you estimate at large N has a scaling dimension of 6.15. And so you can actually try to make this gap pretty big if you trust that large N estimate. Yeah.
Good question, David. So from large N, what's the operator you get for M1 prime?
What do you mean? What is the operator?
Yeah, at large N picture. So you take M1 and you attach something to it?
Yeah, it's like taking M1 and dressing it with some fermions. So so in these papers, they kind of developed a nice kind of oscillator formalism for constructing the Hilbert space at large N, which involves a bunch of creation operators that you can use to construct states. And so you basically take the bare charge 1 monopole and you dress it with some additional fermions. Does that answer your question, or you had something more specific in mind?
Well, I was curious exactly because you have the M1, you dress it, you have the bare M1 monopole, you put the zero modes,
yeah,
then you have the gauge invariant M1, and from that one, do you start from that one to get the M1 prime, or you start from the bare one and you put the zero modes in different?
Yeah, I mean, the systematic way to do it is you just start from the the ground state, and you think about all the ways you could add oscillators to construct a charge 1 monopole with these quantum numbers, and this is the next one. So I can, after the talk, I can look up precisely what the construction looks like, but
and that's the leading order at large N estimate?
Yeah, that's the leading order at large N estimate.
Okay. Thanks.
Plugging in N if equals 4.
Okay.
So if you assume kind of a big gap until the second charge 1 monopole, this basically this peninsula structure that Pufu and Chester saw gets even stronger, and becomes fairly sharp, like a sharp tip that's pointing down, basically the shape of this evolves depending on what you assume about this AA bar operator. But if you allow the AA bar operator to be a little bit relevant, say assume its dimension is bigger than 2.8 or something like that, then you see that the location of this tip is kind of nicely compatible with the large N. So one question we kind of wanted to ask in our study is whether it makes sense to take these large N estimates seriously if you make the working assumption that the large N expansion is converging and higher order terms are smaller than the terms that have been calculated. Does that kind of make sense in the context of the bootstrap? And so that's pointing you to, that assumption would point you to this AA bar operator being a little bit relevant. To kind of check whether that makes sense, we explored various things, but one of them is to compute bounds on the central charge of the topological current. This is the coefficient appearing in the 2-point function of the topological current. And so we computed lower bounds everywhere on this peninsula. So this is showing some contour plots of those lower bounds. At large n, you can calculate this central charge to be 1.56. And that's what's shown in this kind of green highlighted curve. And so you can see that in the left plot, I assumed delta AA bar was bigger than 2.8. And actually that lower bound on the topological current becomes right near its large N estimate in a place which kind of coincides with the dimensions of the monopoles being near their large N estimates. So that seems like kind of an interesting, an interesting coincidence that you might want to take seriously. Another thing we can see from these lower bounds is that the region at the bottom of these plots has very strong lower bounds on this central charge and is kind of likely to be unphysical. So that's another thing that we can conclude. The right plot is showing what happens when you assume AA bar is irrelevant. So then kind of the location moves up a little. Okay, but if you kind of try to take this tip seriously and ask, what does the rest of the spectrum look like? One thing you can do is, assume, let's say we assume the M1 monopole operator is living in somewhere in this tip. So we can assume its scaling dimension is less than 2.6. Then if you do that, then you get some, some closed allowed region in the delta M1/2 delta R plane, where R is the fermion bilinear psi bar psi, the adjoint fermion bilinear. And so you get some kind of interesting island in that plane, assuming M1 lives in the tip of this region. If you go to the very tip, you see that, if you assume M1 is less than 2.5, the scaling dimension of R, in addition to delta M1/2, is kind of forced to be also close to its large N value. So there are a lot of interesting coincidences which happen in this bootstrap method. If you assume, say, one of the scaling dimensions is close to its large N value, other scaling dimensions are also forced to be close to their large N values. Okay, and we kind of checked whether that story is consistent by computing more bounds on these central charges. The left plot shows the SU4 current central charge, and these are contour plots. So it's the lower bound on that central charge is also kind of close to its large N estimate and a little bit lower than it in this region, and similarly to the topological current central charge. We did some extrapolations to kind of large derivative order in the bootstrap. I won't dwell on this, but the basic punchline is that kind of all the extrapolations of the allowed ranges for delta M1/2, delta R, CJ, and CJT, they all seem kind of still compatible with their large N estimates, extrapolating these sizes of these bootstrap islands in the to large derivative order in the bootstrap, which is kind of your conjecture about the optimal island. Okay, the bounds get a little bit stronger if you go to the mixed correlator system and make similar assumptions, but doesn't give anything very dramatic. And just to kind of show you, we had all this uncertainty about the dimension of the AA bar operator, whether it's relevant or irrelevant. In this mixed correlator system, something you can do is try to include that as another axis in your island, the dimension of the AA bar operator. And if you say fix the scaling dimension of M1/2 to be somewhere close to its large N estimate, say 1.02, then you get some island in delta AA bar space, delta M1 space, and delta R space. You basically get some ranges for those scaling dimensions, which are all kind of close to the estimates you get from the large N expansion. And in particular, if M1/2 is nearest large N value, the AA bar operator has to be relevant. So, so this is not kind of a definitive story. What we see here is that if one of the operators is close to its large N estimate, then we get some kind of self-consistent solution to the bootstrap equations. And so that's kind of one scenario. It points to AA bar being relevant, which means that Dirac spin liquids could not be realized on a triangular lattice. So if you got some, say Monte Carlo evidence that it could be, then that would start to, rule out this scenario. And the other scenario is that, the large N expansion is really kind of breaking down, and N equals 4, this, maybe we should take this Monte Carlo estimate of M1/2 seriously, and Dirac spin liquids could still be saved on lattices. So these are kind of two competing scenarios that it sort of focuses your attention on trying to distinguish between which of these is correct. So I think that's kind of an interesting thing to do in future work. So that's basically all I had to say. There's lots more you can do in the bootstrap, like finding other islands for these chiral Ising Gross-Neveu models, as well as variants with multiple scalars like X, Y, and Heisenberg. You can look at larger mixed correlator systems for gauge theories, which could help you really answer these questions about, say, 3D QED. Something I'm interested in doing is looking more at kind of non-local fixed points and how they contaminate the allowed space of bootstrap solutions. And then the other thing I showed you is that there's this nice match you can do between analytical calculations using Laurencian inversion formula and numerics. And so that gives you a very nice playground for trying to refine, both your analytical techniques and your numerical techniques. So I'll stop there. Thanks for your time.
Thanks, David. So the talk is open to questions. So Hanma from Perimeter.
Hello, David. May I ask a question about the emergent SUSY? So, do you regard it as some input to constrain your conformal data, or it's a result we can see from those scaling dimensions?
Yeah, you can take both approaches. So in these islands that I showed, we used SUSY as an input, and that gives you more powerful constraints in the bootstrap, and you get, very high precision determinations of the conformal data.
I see.
In this other approach here, which we did not push very far, you don't assume SUSY in the bootstrap, but you do assume, these kinds of gap assumptions in the spectrum that I've assumed for the other GNY models. Then you get some island which is bigger,
right.
But it's compatible with supersymmetry, and you can see that there's kind of approximate SUSY everywhere in this island.
I have a question, David.
Yeah.
So regarding the monopole scaling dimensions for the NF equal to 4
Yeah.
case, so do you get some bounds that are rigorous in the dimensions? So that's one point I'm confused about.
Yeah.
What can we get at the end of the day from the bootstrap for the monopole dimensions?
For the monopole dimensions.
Yeah, or
So, yeah.
there's nothing you can say because there's no clear island, and yeah, what's the?
I mean, there are certainly some rigorous bounds that are, that you get without any assumptions. Like, there's an upper bound on delta M1, which is, completely solid. And if you kind of, how strong the bounds are depend on the input that you put in. So, I think, I think like this kind of peninsula here that I showed is, used pretty conservative assumptions based on our knowledge of the large N spectrum. So, you'd have to like really badly violate the large N expansion in order to escape this bound. So, but then
it's pretty loose, right?
Yeah.
It's pretty loose for the dimensions.
Yeah, that's right.
But this, okay, regarding the scenario number 2
Yeah.
that you were showing at the end, the Monte Carlo gives 1.2 for the 1/2 monopole. In this island, it seems unlikely, right? Yeah, so the Monte Carlo
yeah.
estimates for the monopole dimensions,
Yeah.
there's some tension, right? With
Yeah. Yeah. Absolutely. There's some tension. So that's
Can you,
something.
can you remind me how they what's the Monte Carlo lattice gauge theory they're using? Like, who's doing this? So what's the reference for this square? You're showing?
Sorry. The reference is Karthik and Narayanan.
Do they just discretize the field theory and put it on a lattice, or is there some more clever?
They do some clever things, but I need to remind myself precisely what they do. Yeah, I'll send you the reference.
But are there like other
Yeah.
other lattice gauge simulations that find similar monopole dimensions, or that's the only reference?
No, that as far as I know, that's the only one.
Right. So
I think, yeah, I think doing more lattice studies of monopole dimensions in QED is kind of important for resolving this. You know, there's a clear tension between this lattice result and the large N calculations at 0th order. So, you know, deciding kind of which of those is correct is pretty important, and the results of that can then inform the bootstrap studies and kind of getting putting these islands on firmer ground.
but somehow my intuition would be that the scenario 1 would be more likely, that the large N does not break down at 4.
Yeah, that's also my gut feeling. That's my intuition. I mean,
your
you know,
intuition has, I guess, more input because you have all the bootstrap data, which seems also more consistent with that scenario. Or am I wrong? Am I biased in this?
No, I think it is kind of seems to be very self-consistent in a highly non-trivial way. You know, if you say M1, you know, like you look at M1/2, you know, the leading correction to its scaling dimension is quite small, 0.038. You know, if the next correction is at the same order or slightly smaller than that, you know, you're definitely led into this scenario that the large N, all the large N data could be pretty close to its estimates.
So what's missing in the bootstrap so that, for example, you could match the precision of the large N for the monopoles, or what's the sort of, is there a next step that?
Yeah, I mean, so I think, you know, what's really missing is you know, a way to basically cut this off from the right. You know, we got these kinds of peninsula structures, and the tips look like they're could be compatible with this large N estimates, but we don't have a you know, a very kind of rigorous way to cut off this region from the right and kind of fully isolate it. And so that's what we need. And the hope is that, you know, maybe by going to some larger mixed correlator systems, you can access, you know, other parts of the spectrum. And if you put gaps in those parts of the spectrum, then that can help you kind of further isolate this solution.
Feasible with tools today, or it's just too heavy at this point?
No, it's, I mean, it's you know, it's feasible. I mean, you know, like I think, you know, last week, you know, Yin Chen showed some very nice results coming from bootstrapping 4-point functions of currents, making connections with some of these gauge theories. And so, you know, that kind of thing it's a big, you know, it's a big computation, but I think it's doable with current methods. So it takes some work, but.
We get an island eventually. That would be really interesting for people.
Yeah, of course. Yeah.
Oh, I see a question, so I'll bring the mic. So Santanu Day from Alberta.
Hi, David. My question is about the QED3 bootstrap, and I was wondering, is it possible to get dimensions for fermionic current operators? U1, a simple U1 current.
Sorry, the fermionic.
J mu, psi bar, gamma mu psi.
So right, so that operator Yeah, that's a good question. So that operator is not expected to be in the spectrum as a primary operator. So, for example, in a perturbative description like Laurencian, you could see that operator is basically removed from the primary spectrum by the equation of motion.
I see. So does that mean that the the gate charge is vanishing, or does that mean the gate charge is infinite? What does that mean physically?
I mean,
minimal coupling.
Yeah, I mean, well, physically here we're only dealing with physical operators that are gauge invariant operators, and none of them carry any gauge charge. But I think that's a really good kind of point, which is that this operator kind of being removed from the spectrum is like the equation of motion for QED, and currently the bootstrap implementations, the OPE channels don't access that sector of operators. And so if you go to a larger mixed correlator system, you might be able to access that sector of operators and impose a gap.
Very interesting.
Yeah, so I think that's a concrete future direction to try.
Very interesting.
I have
May I
a
ask
small question. Oh, well, there's a question from the audience, I think.
Hi,
Amir? Yeah, so David, do you hear the audience question from Zoom?
Yeah.
hi, thank you for your talk. For bootstrapping QED plus Chern-Simon, actually you need the leading order calculation for the monopoly scaling dimension, yes? Or that's the part. I mean, because for bootstrapping QED3, you're using NF equal to 4. What make it hard for QED plus Chern-Simon?
What makes it hard? I mean, so it's right. So the Chern-Simons theories, break parity, and so that means that the OPE structure is different. You can allow parity violating couplings and operators appearing in the OPE which violate parity and so on. And so QED, which is parity preserving, is nice because then you can kind of impose all those selection rules, and it makes the bootstrap more powerful. But in principle, there's nothing stopping you from setting up the bootstrap appropriate to Chern-Simons theories, which allows parity violating couplings, and then you can see how far you can get. But it's kind of an even harder problem than the QED one, which we're already.
Maybe I'll ask one last question. So have you tried varying NF in the QED3 and to see if you get, because at very large end, then clearly there's a solution.
Yeah.
It's a CFT.
Yeah.
How about 5? Like, I mean, is odd NF different for you? So if you just try to sort of move around 4 and see what happens, like
yeah, so
3 or 5.
Right. I mean, one challenge with doing that, you can do it to some extent, but one challenge is that the quantum numbers of the monopoles vary with NF, and they become in kind of bigger and bigger SU NF representations as you go to larger values of NF. And so the bootstrap problem becomes more and more complicated.
Well, the smaller NF, like 3.
I think in the bootstrap you could try to, let me think. Okay, so one thing, so in this work by Pufu and Chester, they computed similar plots for n equals 2, 4, and 6.
But why only the even ones? Like, is there any constraint that in a bootstrap you would have issues? I mean, the odd number, you can realize that at the surface of some.
Let me think. In general, the bootstrap equations can be kind of analytically continued in NF. One thing I'd want to think about is whether you could make sense of the representations of the monopole operators at odd values of NF. I'm not completely sure.
Okay, and the even ones, you were going to say something about the 2, 4, 6. So they made plots in the paper for 2 as well, right? That's what you were saying. Shai and Silvio.
Yeah, that's right. They made
Wow.
plots in the paper for 2 as well. Yeah. So yeah, so you can make plots for two as well. We didn't, push that very far. I think the other thing that I can say is that in, if you do like the bootstrap for say 4-point functions of the fermion bilinears, then there's no problem with kind of continuing different values of NF and trying to continue that down to 2 or 3 and seeing what happens. And you can actually try to you can try to use that as a way to estimate the bottom of the conformal window. Like you compute bounds as a function of NF and ask like where do those bounds, if you can conjecture where you think QED lives in those bounds, you can ask where do those bounds force the leading singlet operator to become relevant. And so that's a method you can use to try to estimate the bottom of the conformal window, and those kind of estimates involve making some assumptions, but they point to the critical value of NF being above 2. And I think there are other methods which point to the critical value being above 2. So that's one of the reasons why we haven't focused so much on.
So is there a bootstrap bound on the window, lower bound for NF critical, or it's something that's too loose to?
There's no sharp bound. You can, one thing you can do is, you can compute some bounds from this fermion bilinear system. You can identify in those bounds some kind of mild kinks, which you might conjecture correspond to QED. And if you track the locations of those kinks down to small NF, then that can give you a way to estimate the bottom of the conformal window, but it's not very rigorous. So putting that on a more rigorous footing would obviously be very, very interesting.
All right, well, thanks for answering all the questions. So I think we can thank David again for his great talk.